the talk I will do today is an introduction to a theory which has been introduced by myself and colleagues around 1990, and which has been quite developed now, and which has expanded in many directions. And I'll basically talk about applications of this theory, not very much about the mathematics which are behind, which are quite complicated, but I think that the applications are quite worth looking at the theory. So the contents of the talk will be, of course, an introduction, and then we'll talk about the definition of what is a differential flat system, and with two main applications. One application will be motion planning, and the second will be trajectory tracking. And I'll illustrate this with a very, very simple application to the startup problem of a DC motor, of a very elementary linear DC motor. And you'll see that even in this case, you can get a very different approach to that than the ones which have been developed until now by engineers. Then we'll talk about linear motors and the problem of oscillating subsystems which are attached to a system, and the way to take this into account in this theory. And then we'll talk about applications to robotics and mechanical systems, in particular some kinds of robots and cranes. And then if I have time, I don't know, because I have a lot of things to present, and I'm not sure that this is able to be compressed in 1 hour. But so there will be an application to aircraft flight control, and then I'll just say a few words about extensions to infinite dimensional systems, in particular to systems described by PDEs and delay systems and fractional systems. Okay, so to introduce the subject, I'm asking the question, what have those very different systems in common? This is a DC drive. This is an overhead crane. This is a robot trying to move an object. This is a high precision positioning system, which is supposed to move in the XY directions in order to for example, to carve some silicium disk, or an aircraft, or a chemical plant, or also many others like magnetic bearings, active suspensions, drones, and so on. So what do they have in common? Apparently not much, but let's look at this very, very simple example. So you take a DC drive whose model can be, well, it's quite simple to modelize with a linear system with the electrical circuit here and the mechanical part here. Okay, so you get you apply a tension to the circuit, and the motor starts turning at a velocity omega, and it is subject to the mechanical constraint due to the energy, to the inertia, and there is a torque constant here, k sub v, which is in general equal to this constant here. Okay, so what's the structure of the system? You control it by U, and it turns out that if you look at the variable omega, which is the angular velocity of the motor, and you call it y, then you can express the intensity of the current as a function of y and y dot, and you assume that the resisting torque C sub r, which is supposed to be a constant, is known. And
KV. What is KV?
KV is the torque constant. So you can obtain I in this by this equation, okay, if you know C sub r, and then you can know U by replacing I by its value as a function of omega here, and you get U by this formula where appears y with successive derivatives up to second order. Okay? So the conclusion is that if you know that variable y, you can reconstruct everything from the motor. Okay? So, and you don't even need to know its dynamics, because its dynamics is completely encoded in those equalities. Okay? Because if you replace y in these equations, and you replace all variables by those formula, then you end up with 0 equals 0. Okay? So there is no more differential equation. And this is basically the main property that is called differential flatness. That means the output y and its derivatives y dot y double dot parameterizes all the system trajectories. Okay? So, what for? Well, first, in all the previously mentioned examples, remember all these examples, they have the same property, that there are particular outputs which describe completely the dynamics of those systems. Okay, and you don't need to even remember what are the dynamics. Okay, so y is called a flat output, and the corresponding system is said to be differentially flat. Differentially because, as you have seen, the parameterization depends on not only on the output but also on its successive derivatives. Okay. So what for? Let me ask you a question. This is a pendulum, and this is a triangle in order to let the pendulation remain orthogonal to this bar, and this is just to visualize the origin. Okay, and then there is a motor here that can turn the whole thing, and the question is, can you turn, for example, the whole platform, let's say 30 degrees at high speed, and at the end get the pendulum at rest? If you accelerate, of course, the pendulum will not remain at rest. It will oscillate. So how is it possible to stop after 30 degrees, I say it's 30 degrees, it could be 45 or 20, never mind. Can you stop without oscillating? So I generally teach that kind of things to doctoral students, and generally I obtain 50% yes and 50% no. But when I ask everybody, they don't know why they answer yes or no. But the answer is yes. You can do it, and I'll show you. And moreover, you can do that without any sensor on the pendulum. Okay, you don't know the position of the pendulum. You only have a sensor on the motor. Okay. So we're trying to move this undamped pendulum at high speed, and we want to have no oscillation at the end and no overshoot, and of course without position sensor. Okay, and then let's see what does in general an engineer in this case. You have a sensor on the motor, so you just control the motor. You want to make a 30-degree displacement, so you control the motor in order to have this, and you don't take into account the pendulum, because the pendulum is considered as a perturbation. Okay? But of course the pendulum will degrade the accuracy of positioning, because since it moves, it will create a perturbation to the motor. Okay? But nevertheless, the classical design will be like that. So this is what you get with the classical design. So the pendulum is oscillating very with a large amplitude. And now let's see what you get with this flatness theory, using the formulas that I was presenting. Okay, so you can choose trajectories in such a way that you start at rest and you arrive at rest at the same overall velocity of displacement. Okay? So, and there are also other techniques. I'm sorry. There are other techniques like input filtering, in order to prevent from unwanted oscillations of the system. But if you apply that, that means slowing down significantly the system. The velocity here is divided by 4 in order to get the same amplitude. Okay? So once again, I'll show you the kind of trajectories that you construct with this kind of theory. This is purely mathematical. There is absolutely nothing from intuition. I mean, that's just applying the formula, and you see that the platform starts steering the pendulum, and then the pendulum goes above the platform, and then the platform is slowing down in order to stop the whole thing. So, and this is something that is done naturally because of the formulas that describe the.
There is no overshoot when it comes back. There is no overshoot.
No. I mean, you said no overshoot. Yeah, yeah, yeah. No, no, no. There is absolutely no overshoot. There could be overshoots if you ask the displacement to be too small compared to the possibilities of the frequencies possibilities of the pendulum. If the frequency at which you want to stop is too small, then of course there will be an overshoot.
You tried, or you know if anybody has tried to solve this with the classical optimal control? Yes, it's like
Yes, of course.
descent or something like that.
But in order to use classical optimal control, you need to measure this position because you want to know when you switch.
Not sure, because if you have a sufficiently good model, the oscillation of the pendulum will go back to the motor. So you have some observability of
Yeah.
the pendulum in your position sensor on the motor.
Yeah, you said if, but this is not the case in general, and no, this is very difficult to. I mean, I made comparisons with optimal control in this case, but you know, when this system is very unstable, if there is a small error when you switch, then this error will propagate enormously. And here there is no such problem.
I'm not sure that the only way of solving optimal control is by assuming switching. There are some other ways of using the
Oh, I mean,
generalization
yeah,
of
yeah, okay, okay.
with not necessarily with just switching. So some of the time
Oh,
the control
yeah,
is
yeah, yeah.
zero,
I mean,
singular arcs.
yeah. No, I was meaning minimum time, but minimum time you get switching. No other way. So, but if you, for example, do LQR or something like that, the linear quadratic, then.
This is totally nonlinear.
Propose that to postpone the
Yeah.
question.
Okay.
Yeah.
Okay. Now another example that maybe can improve the question. You have here a linear motor, which is moving on a rail, okay, and you control this motor and you have the motor position, but there is a mass with a flexible beam attached, and you don't measure it. Okay, so again, you want to make displacements of this motor, and try to make the positioning as accurate as possible. Okay, so if the general engineering approach would be, again, this is a perturbation, and you just make a feedback, for example, PID on the linear motor because you measure its position. Okay, and then, of course, you get this. So very big oscillations, and of course the positioning, the accuracy of positioning is perturbed by those oscillations, and you cannot easily achieve what you want. And by flatness, this is what you get. Okay, and this is again another remark is that this is very easy to obtain and very easy to implement, contrary to the approach with using optimal control. That's okay. I'll give you the design in a moment, but you can say, of course, with one mass, well, I spend one day on the system and I can do that, okay? But now I will show you I can do it with 2 masses, but I could do with 30 masses if you want, okay? So this is what you get, again, with the classical approach. And now with the flatness approach. So since the extra masses are not oscillating anymore when you stop, then the accuracy of positioning is much better. You get an improvement of order 10 times. I mean, in terms of accuracy. Okay. All right. So. Let's now give the definition of what we call flat systems, and then we'll go back to this example and see how it is designed. So you have a nonlinear system, x dot equals f of x and u, with x in a you can without mathematics, you can just say it's n variables, okay, that can live in a manifold or in a vector space, whatever, n-dimensional, and U is the control with m components, m independent components, and of course m is supposed to be less than n, otherwise you have too many controls I mean, there is no more problem because if you have one control for one state, there is nothing to say. I mean, okay. So you say that the system is differentially flat if and only if there exists an output y of the same dimension as the control, such that its successive derivatives y dot, y double dot, etc. are independent, and this means that it is an output, and conversely, x and u, the variables of the system, can be expressed as functions of y up to a certain number of derivatives, of time derivatives, and u the same. Okay? And if you replace now x and u in that differential equation, you get it identically satisfied. Okay? So that means that y is a complete parameterization of the trajectories of the system, and y is called the flat output. And the mapping phi psi, the pair phi psi here, is called Liebeklund isomorphism. Maybe I will have a few seconds to say why we need such a complicated notion of Liebeklund isomorphism, and why usual notions like diffeomorphisms and such things are not enough to describe these. Okay. I just insist on the notation y to the alpha, which means that the first component is differentiated alpha 1 times, etc., and the mth component is differentiated alpha m times, where alpha is the multi-integer, like that. Okay? Now, why is it so interesting for motion planning? What you get is that if you have a system living on a complicated space, on a manifold which has a very complicated shape, these are the integral curves of the system. And what differential flatness means is that there is a space here, which is a vector space, which is the simplest possible space that describes this object, and which is only made of curves. There is no differential equation, no constraints to on the variables here. They are all independent. So if you construct a curve here, you can lift it on the original space and obtain an integral curve. Okay. So now, if you want to go from that point to that point, for example, and you want to know how to do this by choosing the proper control. How do you do that? First of all, you get initial and finite conditions which project on this space, and then you just have to interpolate those conditions here, because there is no more differential equations, and lift it back in order to obtain the right curve. And this is what has been done in the examples that I showed. So this is just explained here, because of this mapping, x and u can be expressed as functions of y dot up to a certain number of successive derivatives. And if you're able to construct the y trajectory, then you immediately get the xu. Okay? So everything remains, the problem remains in describing the way of constructing such a curve, and this is very, very easy. The second important application is how to when you design such a trajectory, how to track it, how to follow it, even if there are perturbations that create deviations. So here at this point, you need to have measurements of the system. This was not applied on the examples that were presented before, but this will be applied after. The main result is that if a system is flat, there exists a dynamic feedback which is called endogenous. I'll say why after. Namely, you can express u as a function of x and a new control v and a new state variable z, which extends the system and which satisfies a dynamics that you can choose. Z dot equals beta of x, z, and v, and you have the choice of beta. Okay. So there, if the system is flat, there exists such a dynamic feedback such that the system becomes equivalent to this simple integrator. Okay. And that means that if you are given a reference, y reference and v reference, satisfying, of course, v reference is equal to the alpha plus 1th derivative of y ref. And if you want to stabilize the tracking error, then you just state that the difference v minus v reference is equal to some polynomial of the some combination of the derivatives of the error in such a way that the coefficients here are such that the polynomial has all these roots on the left half plane, on the left half complex plane. Okay, so that the differential equation, which is here, is stable, and then the error is exponentially decreasing at least locally in certain domain. Okay? I just presented what can be done with pole placement, but you can do the same with other design methods like Lyapunov design or backstepping or H infinity techniques or whatever. Now, let's go back to the startup of a DC motor. You want to start from rest at initial time Ti, and you want to arrive at final time Tf at some stabilized speed omega sub f. Okay? So, what the most classical design consists in you want to start at zero speed, you want to arrive at omega f, then you take as a reference a Heaviside function, a step function, okay, and you wait some epsilon time until you start taking the reference of omega f, and you keep omega f all along, constant, okay? And then you get this as a reference for the tension, for the voltage, and in order to converge to this voltage and reference, you use, for example, a PID, proportional, integral, and derivative. So with the proportional gain, the derivative gain, and the integral gain, okay? And you tune them in order to have the result. And in general, you get some more constraints. You cannot use tensions which are higher than some maximal tension. You cannot have variation of intensity larger than some bound delta, and also some intensity itself that cannot exceed some bound Imax. Okay, so the design will be. I will show you a design with omega f equals 30 round per second. And you want to achieve this 30 round per second in 0.1 second. So it's quite a challenge. You put some error, of course, on the initial frequency, the initial angular velocity, and on the resisting torque. And Umax is chosen to be 25 volts. Imax is 10 amperes. And we'll talk about the bound here, delta, which will play a very important role. These are the gains that have been chosen. Okay, so and we'll give the design for delta equals 100 amperes per second, 95 amperes per second, and 500. Okay, so it's a quite large range. And for 100, you get the following behavior. First, you saturate, and then you oscillate before reaching the omega f objective, and this is the current showing that you saturate, and this is the voltage. Okay, but you can achieve what you want, and you arrive at omega f approximately at 0.1 second.
The constants, are they the result of
No, 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 no. It's satisfying this PID.
How do you choose KP, KD, and KI?
By very classical techniques, by tuning first the KP and then improving by KD and then experimentally, yes, yes. Well, of course, it could be improved. I fully agree. But that's just quickly and that's quick and dirty job. Now, in order to show that this plays a very important role, when you decrease it to 95 amperes per second, then you get it completely destabilized because of the saturation. Okay?
Is ampere per second? What type of what is ampere per second? And how is ampere?
It's the rate of rise of the current.
The rate. Okay.
Yeah. Because you cannot rise the current as fast as you want.
The only difference between the two examples is 5% in the current rate?
Yeah.
100.
Yeah. Yeah. For this, of course, for this tuning, but I think that tuning is not so bad. And now, in order to have absolutely no saturation, you're obliged to reach to increase delta up to 500 amperes per second with that design. Okay, so that's quite important. And now we change this design and go back to the flatness-based design. So in place of taking the Heaviside function as reference, you take a reference which is obtained by flatness, and you start here. This reference, as you can see, is starting from at Ti. This is 0 because you get T minus Ti here, and at Tf, this is equal to 1 because capital T is Tf minus Ti, and this is 3 minus 2 is 1. So you get omega f, okay? So you start from 0 and you arrive at omega f. And you arrive in a polynomial way, so very smooth, okay? It's an S-shaped function. And you obtain the control, the control reference, V star, by using the formulas that were given before, okay? And you take the same PID control as before, but in place of the previous references, you put these references, okay? That's the only change. I keep the same gains, I keep everything the same, but the only thing which is changed is putting Y star in place of omega star. Okay? And then look at what you get. You get something very, very smooth without any saturation, even if delta is 10 amperes per second. Okay? And what's the reason why? The reason why is that at start with the first approach, you have a very big error because you need to go from 0 to omega f, okay? And then the control is saturating immediately, okay? Here you get a very small error at the beginning because you know that you're at rest, because you follow a trajectory which is at rest at the beginning, and thus the initial error is very, very small. And you start tracking it, and you remain in a very small neighborhood around the reference trajectory. Therefore, the error is always very small, and you can tune it very easily. Okay? That's the fact that the error is very small is, let me, yeah, here. That means that those will be, those terms will be close to 0, and you will have almost this, okay? Which is a trajectory, which is generating a trajectory that you're sure to, yeah?
Y star is measurable by a sensor, or?
Yeah, here it is assumed to be measured, yeah.
But this is Y star that you use, not the Y.
No, here.
Okay.
The Y star, of course, is not measured, it's a function of time. But this is measured. Okay, so that's the main difference with the classical approach is the very precise design of the reference trajectories, that you are sure that you can follow them because they are solutions of the system. Okay. Now let's go back to this linear motor. Again, this is the model is very easily obtained. X is the position of the motor, Z is the position of the auxiliary mass, and the stiffness of the flexible beam is K, and its damping term is R. Okay. So how to design a rest-to-rest fast and high precision displacement. As before, we assume that X and X dot are measured, but Z is not measured. Okay, the auxiliary mass is not measured. The classical design will say, I don't want to know what is perturbing the system, and I just take into account the motor. Okay, mx double dot equals the force applied to the motor plus perturbations. And if you want to design a rest-to-rest trajectory, then this is, for example, what you get in order to for the x trajectory, for the motor trajectory. Okay, again, here you ignore what is the contribution of the auxiliary mass. Okay, and this is the force that achieves this reference trajectory. Okay, again, it's a very elementary polynomial design, just by interpolation. And as before, you put a PID controller with the reference here and the proportional, derivative, and integral terms. Okay, and this is what you get. You get the motor reference, an S-shaped curve, and the auxiliary mass displacement. Here you see a small oscillations. And this is the deviation, which is of order 10 to minus 11 meters. I mean, it's 10 times this, so it's of order 10 to the minus 10 meters. And this is the force, and you see that the force goes on a little bit moving, but it's quite satisfactory for a total duration of half a second. But now if you decrease to 0.25 seconds, then the previous design becomes much worse. Okay? So you degrade the accuracy quite significantly if you want to achieve this the displacement too fast. Okay. And now this is the flatness design. In place of x, you design the reference trajectory for the flat output y, and the flat output can be shown to be given by this formula. Okay, I don't tell you how, but this is given by this formula, and x and z and the force are given by those formulas as functions of y, y dot, y, and y up to the fourth order. And now, this is the choice of trajectory that starts from x0 and arrives at x1 in duration capital T at rest. And this is the PID controller, which is the same as before, but here you change the previous reference of x of t into the one that you deduce from this one. Okay, with the with those formula. Okay, so you have y reference, you put it there, and you get x reference, and you get z reference, and f reference. Okay, and then what you get, of course, for 0.5 seconds, you get something quite comparable, but for 0.25, you get something better. If you maybe I can, if you can memorize those curves, for example, the deviation here is about 4. I'm sorry, to the 10 to the minus 10. Okay, and with the other, this was about 2 to 10 to the minus 9. Okay. Okay, so just to tell you how this can be designed, and this is what is finally obtained. Okay. Okay. I could do the same thing with two auxiliary mass. It's just this is an easy adaptation of the previous technique, and you get comparable things. I don't want to insist more on that. Oh. Now, I would like to present some other applications. For example, in robotics, this is a robot with the three main axes, which are controlled by direct drives. Okay, but the two last degrees of freedom, this one and this one, are not controlled. Okay, so you can turn this in this direction freely and in this direction freely, but without drives. Okay, so what you want to do is to start from the stable position and move upwards in the unstable position, and then turn at full speed around the axis, the vertical axis, and then stop, and then go back to the original. Okay, so that's quite a difficult task if you don't use that theory. This is asserted by many roboticians. Sorry. Okay, so you start in the upward position, turn at full speed, stabilize then in the in the upward position, and then stabilize in the backward in the downward position. Okay. Another application is for if you want to move objects with a robot, which is also quite a difficult task. I fully agree that this is just part of the problem, because there is a very big technological problem in order to realize things that work, that are robust, and so on. But at least the mathematical part can be improved with that kind of technique. So you have an object that you want to move, and you have 3 fingers in order to move it, okay? And this is, in order to simplify, this is equivalent to moving 3 planes tangent to this ball, okay? And what you get is this animation. Let me. So here there are the curves which are chosen for the orientation. Okay, you will see that there is a small cross that will evolve as the ball will turn. Okay, so you pass from this orientation to this orientation continuously with this with the motion of the 3 planes. Okay. Another application which is quite interesting, in my opinion, is an application to cranes, because as you have seen, it's possible to compensate for oscillations, and this is a reduced size model of a crane that has been designed for the U.S. Navy in the 30s, and which is still at work on ships in order to unload and upload the materials on ships, on military ships. Those cranes are designed in that way. This is the load, and there is a cable going through this pulley and controlled by this motor. Okay. There is a second cable here controlling the horizontal position of this pulley, and there is another cable controlling the vertical position of the pulley, because otherwise it would fall. Okay. And finally, there is a motor here with a belt controlling the vertical the rotations around the vertical axis. Okay, so the experiment that I propose is there is an ashtray here with a very small hole, and I will follow a parabola and get out of the ashtray and go back without oscillation. Okay. And you'll see that this is just the beginning of the experiments. There is a sequence of things. Okay. And now only the motor positions are measured, and what will be used is the force the force feedback based on the difference of torque of position of the motors. Okay, so you can stabilize without sensors on the load, only with sensors, with position sensors on the motors. Okay, so and finally you follow parabolas around horizontal parabolas and like this. This one is, I think, the most impressive because you have to throw it away and then get it back. Okay. And this is all done with the formulas obtained by Flatness. Okay. Okay. How long do they? Okay. Maybe I have some time to talk about aircraft control. In fact, aircraft control was the first motivation to go into these developments. The idea of flatness became first from this application. So here you have an aircraft. This is these are the usual change of bases, frames, and the change of the angles associated that describe the various frames that we need. You have the frame on Earth, Y1, Z2, and Z0 are represent the. Let me see. No. I'm sorry. If you change x0 to x1, z0 you turn around z0, and okay, I don't want to say complicated things, and I don't remember exactly the order where I design things. So, and of course it depends on the order. So I don't want to bullshit this. Okay, this so the forces applied to the aircraft are the thrust. There are, of course, the weight and the aerodynamic forces which act on the aircraft, and this is the velocity of the aircraft. The x sub b is the body longitudinal axis, and alpha, this angle, is the incidence angle. Beta is the slipping angle, because the aircraft can have a velocity different from the body axis, and you get the rate of turns P, Q, and R here, P, Q, and R, and the moments associated, which are L, M, and N. Okay, then G is the gravity. I'm sorry.
What's the point G? Is the
G is the center of gravity. Yes.
the 1-point model. Yes.
Yes.
Like infinitesimal aircraft.
Yeah. Of course, this is just an idealization. And then the classical 12-dimensional system is given by those equations, which are a little bit complicated if you don't, if you're not used to them. But you'll see that, in fact, the structure is very simple. Why? Because if you happen to know x, y, and z, then you can immediately obtain the velocity and the angles chi and gamma, just by inverting those formula, okay? And then if you have v, chi, and gamma, you can invert those equations and get mu and other variables that I'll show you later. But you can do it progressively in order to get everything as functions of x, y, z, and this angle beta. Okay? This is just to precise how are the forces x, y, and z as functions of the state, and in particular as functions of the angles alpha and beta, and the moments L, M, and N, which are acting, which are making the whole thing rotate. And the assumption is that the forces x, y, and z here in the coefficients here depend on the altitude, on the velocity, on the incidence and slipping angle and the thrust, but don't depend in a significant way on their derivatives. Okay, this is what is generally assumed in aeronautics, and the same for the moments L, M, and N. The only difference is that those coefficients depend on the angles delta L, delta M, delta N, which are the angles of the surface controls. Okay. And this is the dynamics of the surface controls, controlled by the motors. And here, at the end, you get full controls, which are the thrust F and the control surfaces. Okay, and you get that the system is flat. The flat outputs are written in red, x, y, z, and beta. And from x, y, z, and beta, by differentiating once, you get v, gamma, and chi. By differentiating 2 times, you get alpha and mu knowing beta. Okay, and you differentiate again, you get the velocity angles, PQR. And you differentiate again, and you get the surface controls, and then differentiating again, you get the voltages applied to the motors. Okay, and from here you also get the thrust. That means that if you summarize all the system variables, which are velocity, incidence angle, the Euler angles, gamma, chi, and mu, the velocity angles, PQR, delta L, delta N, and so on, they are all expressible in functions of x up to 5th derivative, y up to 5th derivative, z again up to 5th derivative, and beta up to 3rd derivative. Okay, that means that the system is flat, and that means that you can deduce immediately from that if you just take this as a new control, this as a new control, this as a new control, and finally this as a new control, then the system is just x to the fifth equals to v1, y to the fifth equals to v2, z to the fifth equals to v3, and beta to the third equals to v4. That's all. Okay, so you get a very simple linear system equivalent to that if you are able to invert all these relations. Okay? And then if you want to follow to design a reference trajectory, you can choose trajectories of that form and compute the coefficients AXK, AYK, AZK, and so on by interpolation. Okay? And then I'll just make a very rough comparison between a coordinated turn, which is done by any pilot as it is taught to any pilot, and this is the corresponding maneuver with the flatness-based approach. What happens with the usual coordinated turn? You're in constant altitude and constant speed. You're traveling at constant speed, okay, and you want to make a turn in order to arrive at this point. So you construct a circle with a given radius here, and which arrives tangent to your velocity line, okay? And what happens at the tangent contact here? What happens is immediate. This is a line, so the second derivative is 0, okay? This is a circle, so the second derivative is a function of the radius, okay? So that there is a discontinuity at this point of the second derivative. And this discontinuity, if you're not cautious enough with the design in the gains in your controller, then they will produce some overshoot in the best situations, and maybe worse. Okay, and so this point will be at a source of problems. But here again, you design by interpolation a curve that you can follow without any discontinuity. Okay, so you'll do it in a much smoother way with here designed with 7th degree polynomial and 3rd degree polynomial. In fact, this 3rd degree polynomial will be just 0. You don't need to, yeah?
The turn is in the horizontal plane. The aircraft goes like this, just changing its pattern, or is it in the vertical?
No, it's in 3 dimensions.
Okay.
This is in 3 dimensions. You have x, y, and z. Okay. Yes, of course, because if you turn, you lose altitude. Of course.
And the result, the low one, is it the coordinated term?
You cannot call it.
The lateral acceleration on the pilot is 0 all the time?
No. It can be small, but it's not 0.
So it's good for UAVs. It's not so good for manned aircraft.
That's right. I fully agree, but it's good for the performance of the aircraft.
There's no 0 on this curve, on the second curve?
No, it's never 0, exactly 0. It's always small, but this is never a circle. That's why. Of course, the pilot here, once this point is passed, then the pilot is more comfortable here, of course. But the difficulty is to pass this point. Okay? just to finish now, some extensions to infinite dimensional systems. Up to now, we have designed reference trajectories and tracking for finite dimensional systems. Now, this is an example of a flexible pipe, which is used. You know that now, in order to pump the oil in deep waters, in deep sea, you can go up to a depth of 3,000 meters. Okay, and in order to connect the wellhead to the boat, which is trying to, or to the station where the oil is pumped, you need to control what is called the riser, which is considered as which is in a metallic pipe, but at this length it becomes very flexible. You know, it can move in any direction with it's like with this scale, the flexibility is comparable to how do you say caoutchouc? Rubber, right. Okay. So we have made with the French Institute of Petroleum a setup in order to prove that things are possible to improve in this wellhead connection by designing a water tank with a pipe here in rubber. The wellhead is here. There are two cameras that can visualize the wellhead, and there are motors associated to the control on the top. But this platform is perturbed by the wave, which is featured by three motors moving in the three directions. Okay, and of course the wave, the controls of the motors featuring the waves are not known by the controls using for the riser. And so I won't explain the partial differential equations, but what you get is here. By taking an approximation by the two first horizontal modes and the vertical mode of order 0. This is not controlled. This is just to show the waves, okay? The influence of the waves on the riser. And I'll tell you when the riser will be controlled. You see, it even goes out of sight from the camera, and it doesn't matter. Well, now it is controlled. Okay, so you get a connection very, very quickly. You know that in practice, that kind of connection can take 2 or 3 days on real sites, and with that kind of approach, it can take say half an hour. So it's a lot of money which can be saved. Okay. There are also extensions by the notion of pi flatness for delayed systems. There is also a notion of fractional flatness for fractional systems. I mean, the system being described not by an ordinary differential equation, but a differential equation where the order of derivation is non-integer, okay? And this can be used in order to control the heat equation. Okay. Thank you very much.